Welcome for the class. So till time in last class we have completed the two major types of compressors. Initially we had considered centrifugal compressor, and then we had seen axial compressor, which are the parts of gas turbine power plant. Now we will be seeing the next important component, which is turbine. So for that all sake, today's class is basically upon axial gas turbines. So axial gas turbines will be connected to the compressor, rather compressors will be connected to the axial gas turbines, such that turbine will deliver the necessary power required to run the compressor. And we had seen in our earlier discussion that turbines will be having the favorable pressure gradient in the direction of the flow. So what would happen is, we don't need to worry about the losses which would occur due to bound layer separation, since there is favorable pressure gradient. So number of stages in the turbine would always be lower than the number of stages in the compressor. However, we are interested to find out certain performance aspects of the axial turbine from the basic elementary theory of the axial turbine. So as we can see that axial turbine would be composed of again two parts. One is called as nozzle and other is called as rotor. So in between in the axial turbine itself, we are having two components. Every stage of axial turbine is comprised of two major components. One component is called as nozzle, other component is called as rotor. So when the flow enters into the nozzle, as the name suggests, nozzle's job is to increase the kinetic energy of the flow. Here we expect the flow should have decrement in pressure and increment in velocity. So this high velocity flow would flow over the rotor. It is exactly opposite as in case of compressor. In case of compressor, we had again one stage of compressor was comprised of two components. One was rotor and one was stator, but the rotor was upstream and stator was downstream. But in case of turbine, nozzle is upstream and rotor is downstream. Again, nozzle, whatever we are talking about, is the component of the stage of a turbine which is a fixed component, so it does not add any work, does not add any energy to the flow. Rotor is a moving or rotating component of the stage, and it takes away the energy, it takes the work of the flow. That is where we expect the work to be done by the turbine. So this is what one stage of the turbine would be composed of. So 1 to 2 is nozzle, 2 to 3 thermodynamically is the rotor. We had seen that this turbine, which is axial turbine, will be fixed inside the rotor using such an arrangement. We had discussed this point when we were talking about the difference between radial and axial machines in one of the classes. Okay. Now we will be knowing that there are two basically components, two basically types of the turbine. One is called as impulse turbine, another is called as reaction turbine. In the gas turbine, we know that we are having nozzles which are green in color over here, then we have having rotor which is red in color over here. Similarly, in reaction turbine also we will have nozzle in green color and we will have rotor in red color. So this is moving in the upward direction, that is what it is rotating in this direction. So in case of impulse turbine, flow while after coming out of the nozzle, it will directly get imparted on the turbine blade, as what we would see in case of hydro turbines. So in case of hydro turbines, water jet would impart its energy, it will impact on the blade, and then water turbine will rotate. Same thing in gas turbine. Here we expect that the flow should be imparting its force on the blade, and blade would automatically as a outcome of that force, this blade would rotate. But in case of reaction turbine, motion is smooth in the rotor blades. There is abrupt change in the motion in case of impulse turbine, but in case of reaction turbine motion is smooth. We can see the reaction nozzle like this, where jet is coming out in one direction and then we would have rotation accordingly in opposite direction. Same thing here, flow is going in downward direction and then blades will rotate in upward direction. So this is a general diagram for the impulse and reaction turbines. Okay, so as what we would see that there are two components, two types of turbines which are gas turbines. One type of gas turbine is called as impulse turbine and other type of gas turbine is called as a reaction type of gas turbine. So in these gas turbines, as what we had seen, there is nozzle which is green in color, then there is rotor which is red in color. In the same case here as well, in reaction turbine, green is the stator or the nozzle and red is the rotor. So in case of impulse turbine, fundamentally the motion would be governed as what we can see in case of water turbine, where jet of water would impart the force on the water on the blades of the turbine and then the blade will rotate. So here as well, the nozzle will generate high kinetic energy flow and then the flow would get hit to the turbine blades, and due to which the turbine moves in upward direction. In the figure means it would move in this direction to us. So similarly in case of reaction turbine, we have green as nozzle and red as the turbine blades, and the dynamics is same thing as the jet over here, where jet is coming out from the sprinkler in one direction and as a reaction the rotor is rotating in opposite direction. So same thing, nozzle would pass the high pressure pass the low pressure high velocity flow toward the turbine blade, but here motion or movement of the flow is smooth in the turbine blades, unlike in case of impulse turbine where we will see that there is abrupt change in the streamline pattern, but here streamline is moving smoothly in the turbine blades, but here flow is moving in downward direction and as a reaction there is rotation of the turbine blade in opposite direction. So this is how the impulse and reaction turbines are operating for the gas turbine. So now having said this, we will see now how we can draw the velocity triangles for the general gas turbine, which would be either impulse or reaction. So let us draw a schematic of the first nozzle. So let us say we are working with the nozzle. So let us draw a schematic of the nozzle. So let us say that this is our nozzle, and in case of nozzle these are our blades. These are our nozzle blades which are actually having conversion portion. The flow is taking place in the nozzle which are having convergent portion. So this is nozzle. So what we would have is the velocity of the flow which is coming out like this. So this is absolute velocity C2, but we are having rotor which is moving in the direction like this. So we are having basically rotor blades. We are having, so the flow is approaching the rotor with absolute velocity C2. So let us draw the rotor blades. So rotor blades are like this. In case of compressor, we had seen that there is small deflection when the flow passes the rotor, but in case of turbines there will be large deflection. So what would be happening here is basically we are having u velocity, of the flow in this direction. So that is giving us relative velocity, which is, so from the nozzle flow is approaching the rotor with absolute velocity c2. So let us draw the rotor blades. So rotor blades will be like this. We had seen that the rotor blades would lead to very small deviation in case of the axial compressors, but in case of axial turbines there would be large deviation to the flow, since we are having favorable pressure gradient. So this is the V2. So we are having state 1 here, we are having state 2 here, we are having state 3 here, and this is rotor. So u is the velocity by which rotor is moving in this direction. So this is inlet velocity triangle. So practically what we would have is this as, this is V2. So what we would have is this as CA2, and what we would have is this as CW2. So now we are at the outlet. In the outlet also we are having same u in the same direction, and then we have relative velocity first, which will be coming out for the flow, and we will have absolute velocity. So this is V3 and this is C3. So this is how our velocity triangle would look like. So then in the presence of this velocity triangle at the outlet, we again would have CA3 and we would have this as CW3. So this is the velocity triangle at the inlet and outlet for the axial compressor turbine. So now if we combine these two velocity triangles, then u can form a common base. This is u, and then in the presence of u, as what we can see, this is C2 and then this is V2, and then we are having this as CA2, and then we have this as CW2, where we would have this as beta 2 and this as alpha 2. So then we are having this velocity as V3, this velocity as C3 as a virtue of this. So we should have the height of the turbine, height of the blade, we should have the height of the triangle should be same at the inlet and at the outlet, since we expect the flow to be going in the same axial direction with same velocity. So this is V3 and this is C3. So for us this becomes CA3 and then this becomes CW3, and we expect CA is equal to CA2 is equal to CA3. So we expect the velocity in the axial direction should be same or constant at the inlet and the outlet. So here we can see that CW2 is in this direction and CW3 is in this direction. So this should be remembered since we would need this. So having said this, let us consider what is u from inlet velocity triangle. From inlet velocity triangle, u is equal to Ca into tan alpha 2 minus Ca into tan of beta 2. So from inlet velocity triangle, u is equal to Ca into tan of alpha 2 minus tan of beta 2. So u is equal to Ca into tan alpha 2 minus tan beta 2. So u upon Ca is equal to tan alpha 2 minus tan beta 2, and this is from inlet velocity triangle. Now let us consider outlet velocity triangle. There we have Ca into, then here we will have this as beta 3, this as alpha 3. So we would have Ca into tan beta 3 minus Ca into tan alpha 3. Okay, so we would have this is equal to Ca tan of beta 3 minus tan of alpha 3. So we have u upon Ca is equal to tan of beta 3 minus tan of alpha 3. So this is from outlet or exit velocity triangle. So from inlet and outlet velocity triangle we can get u upon Ca is equal to tan alpha 2 minus tan beta 2 is equal to tan beta 3 minus tan alpha 3. So this leads to the fact that we have tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3. So this is a known identity, or rather a famous identity what we have obtained from the inlet and outlet velocity triangles. So now we will find out what is Ws, which is shaft work or stage work for the turbine. We know that the formula is m dot into Cwu into Cw2 minus Cw1. That is what the formula we had derived for, but in that case W was the work input to the system, but we had found out that for the turbine it is m dot into U into Cw1 minus Cw2. That is the formula what we have obtained from the Euler turbine pump expression. So W is equal to m dot into U into Cw2 minus Cw3. This is the stage work for the turbine, but here we can see that Cw2 and Cw3 are in opposite direction. So we have m dot into U into Cw2 plus Cw3. So this is in general. Then we can write Cw1 is equal to 2 is equal to m dot into U Ca tan of alpha 2 plus Cw3 is equal to Ca tan of alpha 3. So we have this Ws is equal to m dot into U into Ca tan of alpha 2 plus tan of alpha 3. So this is what we have got. Further we can know from this relation that tan alpha 2 plus tan alpha 3 is equal to tan beta 2 plus tan beta 3. So we can also write it as m dot UCA into tan of beta 2 plus tan of beta 3. So this is what the stage work expression what we would need for the calculations, or we should know from how to obtain stage work, turbine work from the velocity triangles. Having said this, we should now find out what is the temperature drop in the turbine and what is the pressure rise in case of turbine. So let us take this expression and we would write down this expression again, where we have seen that is equal to m dot into U into Ca into tan of beta 2 plus tan of beta 3, or Ws is equal to m dot U Ca tan of alpha 2 plus tan of alpha 3. So this is what expression we had found out. So now we know but that W dot S is equal to m dot into Cp into delta T naught stage, which is equal to m dot Cp into T naught 1 minus T naught 3. So this is the temperature drop in the stage. So we know now temperature drop in the stage is equal to U Ca upon Cp into tan of alpha 2 plus tan of alpha 3. So this is temperature drop in a stage, or temperature drop in a stage we can also write UCA upon Cp into tan of beta 2 plus tan of beta 3. We can write down either expressions for the temperature drop in a stage. Now we know stage efficiency or isentropic efficiency of turbine is equal to temperature drop, rather we can write it in terms of work, which is actual work divided by ideal work. So actual work is T1 minus T3 divided by T1 minus T3 dash. So we have this as we would also write it as T01 minus T03 divided by T01 minus T03 dash. So here we can take T01 minus T03 dash is equal to 1 upon isentropic efficiency T01 minus T03. So expression for T01 minus T03 is here. We will name it as number 1. So we can take common as T01. So T01 1 minus T03 dash upon T01 is equal to 1 upon stage efficiency into delta T0 stage. So we can write down it as 1 minus T03 dash upon T01 is equal to 1 upon T01 into stage efficiency delta T0 stage. So we have T03 dash upon T01 is equal to 1 minus T0 into stage efficiency into delta T0 stage. But this is P03 upon P01 bracket raised to gamma minus 1 upon gamma is equal to 1 minus T0 into stage efficiency into delta T0 stage. So we can write down this expression as P03 upon P01 is equal to 1 minus T0 into stage efficiency into delta T0 stage bracket raised to gamma upon gamma minus 1. So this is how we can find out the pressure drop into the turbine by the virtue of work interaction into the turbine. So here we would need a help of equation 1 to put the delta T0 stage. So there are two parameters which one should know while working with the turbine, and first parameter is called as blade loading coefficient, and it is denoted by psi. Its expression is stage work divided by half u square. So this is equal to, this is specific work. So what we would have is no m dot here, so we would have it as Cp into delta T0 stage divided by half u square. Delta T0 by stage we can put it over here and we can calculate what is the psi or blade loading coefficient in case of a stage of the turbine. Similarly, there is other constant which is called as flow coefficient. and it is termed as phi, and phi is equal to Ca by u. So Ca by u is equal to phi. So we can write down our expression of psi as 2 Cp. Delta T T naught S is u into Ca divided by again Cp into tan of beta 2 plus tan of beta 3, and then this is divided by u square. This is divided by u square. Delta T naught u square, and then we would have psi is equal to Cp would cancel, then we would have psi. We can define psi in terms of phi here, where we can get 2 into Ca by u is phi into tan of beta 2 plus tan of beta 3. So this is what the expression between relation between psi, which is blade loading coefficient, and relation with phi. So this is how we can write down the expression. Okay, so we will need these things when we are going to work with some examples in case of the axial turbine. Okay, so now next point to be discussed is the TS diagram for the axial turbine. So for TS diagram, we know that we will write down our schematic as what we did for the compressor. We first have nozzle, then we have rotor, 1 to 2 is nozzle, and then 2 to 3 is the rotor. So we know that what is going to happen in turbine. In the nozzle, we would have pressure decreased, and in the stator, if we are having impulse turbine, then we would have pressure to be constant. But if we would have reaction turbine, then we would have it to be continued to decrease. So this is pressure. If we are having velocity, then velocity would be increased in the nozzle and velocity would be decreased in the rotor. Okay, this is C. And then we are having total temperature. Total temperature is constant in the nozzle and it would decrease in the rotor. Okay, so static temperature would decrease in the rotor, and then it would again depend upon the type of turbine. If it is impulse turbine, then it is constant. If it is reaction turbine, then it will decrease. So in the reaction turbine, basically we don't have any enthalpy drop in the in the case of impulse turbine, we don't have any enthalpy drop, or we don't have enthalpy to be converted into kinetic energy in the rotor. Having known this, we can draw the TS diagram for the turbine. So we would be here TS. So first we are in stage 1. Okay, stage 1 to 2 is nozzle. So in the stage, and then 2 to 3 is the rotor. So we are having nozzle here, we are having rotor here. So in the state 1 we are having P1 pressure, at the state 2 we are having P2 pressure, at the state 3 we are having P3 pressure, and this is T1, this is T2, and this is T3. But we can again put associated velocities here. So we can put half C1 square upon Cp such that we can go to T naught 1, and then we would have P naught 1. But we have no energy interaction between nozzle in the nozzle, so we would have same total temperature in the case of nozzle exit also, except that due to friction total pressure would decrease. So this is P02, and then we would have somewhere T03, P03. So we would have P03 here, and then this would be our T03. So this would be our T03. So and this is actually half C2 square upon Cp. This is half C3 square upon Cp. So if we would have gone isentropically, then we would have been reached here in the same P03 from P01. So this would have been the turbine work in ideal condition, but this is our turbine work in real condition. Okay, so this is turbine work in real condition. So this is the velocity TS diagram for the turbine, which axial turbine. So we should know this point, but however this TS diagram has an assumption that we are working with the reaction turbine. If we would be working on the turbine which is impulse turbine, then 2 and 3 point would be same, since there is no enthalpy drop in the process 2 to 3, but we would go little right, since there would be friction loss. Now we will go to the next part, which is degree of reaction. We have defined R as degree of reaction, and then so R is our degree of reaction. So we have defined R is equal to temperature drop in the rotor divided by temperature drop in the stage. This is what our definition of R is. So we will multiply Cp on both sides, so we get R is equal to Cp into delta T into rotor divided by Cp into delta T into stage. We have seen that static and total entropy temperature change would be identical as what we had seen in case of compressor. So R here, this is Cp into delta T in rotor, delta T of rotor divided by stage work. So now we know the stage work formula. W stage is equal to Ca into U into tan beta 2 plus tan beta 3. Ca into U into tan of beta 2 plus tan of beta 3. Now we need to find out what is delta T across the rotor. So how to find out? So we can go to the velocity triangle, or from the TS diagram we know one point, that as the absolute total temperature doesn't change in case of the nozzle, similarly relative total temperature doesn't change in case of the rotor. So relative total temperature means H2 plus V2 square by 2 is same as H3 plus V3 square by 2. So we have H2 minus H3 is equal to V2 is equal to V3 square by 2 minus V2 square by 2. So this expression we can use to find out R. So R is equal to half V3 square minus V2 square by 2 divided by shaft work or stage work. So R is equal to half V R is equal to V3 square minus V2 square upon twice shaft work. So we can go to the velocity triangle and then find out what is the V3 and V2. So V3 can be written as, from the velocity triangle, V3 is this, V3 can be written as Ca tan beta 3 and V2 can be written as Ca tan beta 2. So we can write down these expressions. It is Ca sec beta 3, it is Ca sec beta 3, it is Ca sec beta 2. So these are the expressions for the V3 and V2. So we would have Ca square sec square beta 3 minus Ca square sec square beta 2 divided by, we have an expression Ca into U into tan of beta 2 plus tan of beta 3. So we have R is equal to Ca square upon Ca into U into sec square beta 3 minus sec square beta 2 divided by tan of beta 2 plus tan of beta 3. So R, we can express this sec square theta in terms of tan square theta, and then ultimately we would get Ca upon U into tan of beta 2 tan of beta 3 minus tan of beta 2. So this is, we just have forgotten 2 here. So we have R is equal to Ca upon twice U tan of beta 3 minus tan of beta 2. But we know that Ca upon U is equal to phi. So phi upon 2 is equal to tan of beta 3 minus tan of beta 2. So this is the expression for degree of reaction for the axial compressor, the turbine. So here we should keep one point in mind, that as what we had seen, we are working on the mid blade height. So here all the velocity triangles are drawn at the center of the blade. So inlet velocity triangle is drawn at the center, outlet velocity triangle is drawn at the center. So we don't consider any radial velocity to the flow, and we expect the Ca to be same between inlet and the outlet of the turbine. So we had seen one more thing in last class when we were working with the compressor. We had seen that there is a concept called as free vortex condition. So in the free vortex condition, we were having a constraint, a condition achieved, which was Cw into R was constant. Using that condition, we can translate the velocity triangle drawn for one case to the velocity triangle drawn for the other height. So that we can take an help. So what is Cw for that all six? So we can see Cw2 into R2 is equal to constant. So from the velocity triangle we can find out what is Cw2. Cw2 is equal to Ca tan alpha 2. So we can write down this expression for Cw2, which is equal to Ca tan alpha 2 into R2 is equal to constant. So basically we can, Ca is a constant, so we have R2 into tan alpha 2 is a constant. Okay, this is from free vortex theory. So what we are having is, if we are at the mid blade height, then R2m into tan of alpha 2m is some constant k, and I want to work at some other height, maybe R2 dash. So into tan alpha 2 some dash is also k. So we can find out tan alpha 2 dash is equal to R2m divided by R2 dash into tan of alpha 2m. So we can find out what is tan alpha 2 at some other height when we know the radius of that height, and if we know what is tan alpha 2m at the mid blade height. So this is what we can utilize the concept of free vortex theory to translate the velocity triangle from one stage to the other stage. But there is one more thing which we have derived, and that was tan of u upon Ca is equal to tan of u upon C is equal to tan of alpha 2 minus beta 2. So we can use this concept, u upon Ca is equal to tan of alpha 2 minus tan of beta 2. So this concept we can use, and then we can find out beta 2 at some other radius as well. Since Ca is constant, alpha 2 is evaluated, and u can be found out based on the radius and omega. So this is how we can work out to find out different angles. If they are known at one height, we can find out them at some other height. Okay. So next thing what we need to find out is, apart from the condition of free vortex, there is one more condition for which nozzles are generally, for which axial turbines are designed. It is called as constant nozzle angle. We had seen in last class that there is an expression which says that dH0 by dr is equal to Ca dCa by dr plus Cw dCw by dr plus Cw upon r square plus Cw square upon r. So this is the expression we had seen. But now in case of the constant nozzle angle, we expect alpha 2 to be constant. So for that all sake, we would consider that cot alpha 2 is equal to Ca2 upon Cw2 is equal to constant. And since it is a constant, we can have it same at different altitudes. So we have Ca2 is equal to Cw2 cot alpha 2. So we have dCa2 upon dr, it is a constant, into dCw2 upon dr. Okay. Then we can use this term in equation number 1. So we would have dH0 by dr. This expression we had earlier proved in case of the axial compressor. So cot alpha 2 into d sub w2 by dr plus Cw into d sub w by dr plus Cw square upon r. But Ca is equal to this from equation 2. So dH0 by dr is equal to Cw into cot square alpha 2 into dCw2 by dr plus Cw into dCw by dr plus Cw square upon r. We can consider left hand side to be 0 by fact that H0 is not changing with respect to r. So we can divide the expression by Cw, then we can get dCw by dr into cot square alpha 2 plus 1 into Cw is equal to plus Cw upon r is equal to 0. So we can have an expression which says that dCw2 upon Cw2 is equal to minus minus 1 plus cot square alpha would get adjusted, and then 1 sin minus sin square alpha 2 into dr by r. Upon integration, this expression can be written as Cw2 into r raised to sin square alpha 2 is equal to constant. So, this expression, which is Cw2 into r raised to sin square alpha 2 is equal to constant, is a condition where constant nozzle angle will be maintained at the entry to the rotor. Okay. So, these are the different aspects for the axial turbine. First, we had considered how the axial turbine has different components, how the flow would take place depending upon the degree of reaction of the turbine. If it is impulse, then there would be certain type of the flow. If there is reaction turbine, then certain other type of the flow. Then we drew velocity triangle for the axial turbine. Knowing the velocity triangle, we found out the work interaction, temperature drop, pressure rise. Then we defined two parameters, one is blade loading coefficient and other is phi, which is the flow coefficient. Using this concept, then we drew the TS diagram for the turbine. After TS diagram, we tried to derive an expression for degree of reaction in case of the axial turbine in terms of the parameters of the axial turbine. And then we found out how to find out, if we know the velocity triangle at one state, then how to find out it at the other state using the constant free vortex condition. And now if we know constant nozzle angle condition, then what is that? This is similar to the condition what Cw into r is equal to constant, which was free vortex condition. Instead of that, we have Cw2 into r raised to sin square alpha 2 is equal to constant. So, here we end the part what we were discussing about, which is axial flow turbines. Thank you.